Hello guys, welcome to another tutorial. In this tutorial, we want to draw the shear force diagram and bending moment diagram for this beam and also indicate the critical values of the values at critical points. The question is draw the shear force and bending moment diagram for the beam loaded as shown in figure 1, indicating values at critical point. This is the figure. It comprises of A, B, C, D, E, F, and G. We have a point load of 20 kilonewton at B, a UDL of 15 kilonewton uh, per meter between C and D, a point load of 25 kilonewton at E, and point load of 12 kilonewton at point G. Now, step number 1 is determination of reactions. And I want to make it clear, if you want to determine the reaction, you only determine at the point where we have the supports which are coming down, coming from the downside of the beam. For example, here we can only determine reaction at point A and point F because it is at those 2 points where we have the support for the beam. But all the others are external load which are trying to destabilize the beam. So get it clear, we only calculate the reaction at points where beam is being supported from the downside. Now, how do we determine the reaction? To determine the reaction, we make one support as a reference point. For this case, we are taking support A. Now we want to compute the moments about support A. Let us look at it clearly. Now, if I have support A, and I want to compute, I know the sum of moments is equivalent to 0 because it is a pin or simply supported joint. Now, this is how we shall proceed, and I will advise you to follow this way of doing things. What I'll do, I will find all the forces which have moments acting the same direction with reference to A. I add them together, and I equate that value to the sum of moments from forces which are acting contrary to the other forces. This is what I mean. For example, if I take point A as a reference, so if I take point A as a reference, this point A here, you will find that 20 kilonewton load at point B is trying to rotate the beam to go to clockwise direction. Now assume you have held your beam at point A. So this 20 kilonewton will try to move the beam towards the clockwise direction. If I come to this 15 kilonewton per meter UDL, it will also try to move the beam towards clockwise direction, the same to 25 kilonewton and same to 12 kilonewton. But if you look at reaction at F, remember it is acting upward. Now it is trying to move the beam to the anti-clockwise direction. That is why I'm telling you now what I'll do. I will sum up the moments due to all forces which tend to make the beam go to clockwise direction, and I equate them to the moment due to the forces which try to make the beam go anti-clockwise, because you know the sum of forces, the net moment is 0. Now this is how we shall proceed. Now we'll start with 20. Remember our reference point is point A. So our reference point is A. This will mean that moment due to this 20 kilonewton, it will be 20 times 1.5, because we know moment is given by value of force multiplied by perpendicular distance. Now, for the case of UDL, I want it to be in, first of all, I have to convert the UDL into a point load. How? I take 15 kilonewton per meter, I multiply by a span of 2 meters, I will get 30 kilonewton. Now, remember that kilonewton is acting midway. It is acting at 1 meter, the middle of CD. So now the distance will be 1.5, that is AB, plus 1.5 BC, plus 1 meter to the middle of CD. So this will give us a distance of 4 meters. So this 15 is UDL, 2 is to convert it to a point load, and 4 is the distance from point A, our reference point, to the middle or to the point where the converted UDL act. Then you go to load of 25. 25 is acting at point E. Now, we measure the distance from A. This is 1.5 plus 1.5. 3 plus 2 is 5 plus 1.5 is 6.5 plus this point load of 12 at G. Its distance from A, remember, is the reference point, is 1.5 plus 1.5, that is 3 plus 2, 5 plus 1.5, 6.5 plus 1, 7.5 plus 1, 8.5. So these forces are making the beam move to clockwise direction. So I will equate to, now I assume reaction at A is RA, reaction at F is RF, is equivalent to RF. Remember, RF is the one opposing all of them. RF times the distance from A for RF is 1.5 plus 1.53 plus 2, 5 plus 1.5, 6.5 plus 1, 7.5. Now from there, RF is the only unknown, so I divide each side by 7.5. I will end up with my RF being 55.27 kilonewton. But we know that the sum of upward forces, that is RA and RF, is equivalent to the sum of downward forces. Sum of our downward forces include a point load of 20 kilonewton, a UDL of 15 kilonewton per meter, a point load of 25 kilonewton, and a point load of 12 kilonewton. Now, something I need you to understand is that we cannot equate 15 kilonewton per meter to the sum of RA and RF. We have to convert it to a point load. How do we do it? We take 15 times 2. In short, I mean RA plus RF is equivalent to 20, which is a point load. 15 times 2, because it is per meter and it spans over 2 meters. That's 15 times 2 plus 25 plus 12. Now, in so doing, you find the value of RA will be 87, which is the sum of downward forces minus 55.27, which is the value of RF. So RA will be equivalent to 31.73 kilonewton. Now, if I want to draw the shear force diagram, this is how I will start. I will start with the point A, which is RA, it is here. Now, what I normally do for my shear force and bending moment diagram, I will come and indicate. Now, I will assume this line AG, it is the zero line on number line. So whatever comes on top of that line is positive, whatever comes down is negative. So take it as number line. So this is like y-axis, and this is the x-axis. Then I indicate SFD kilonewton. So I don't have to put here 31.73 kilonewton, because I already show that this is shear force diagram with the lower part of line AG being negative, the upper part being positive, and the values are in kilonewton. I will start with point A. At point A, I have RA, which is 31.73. So I will stand here at A. I move up because it is a positive 31.73. Now, between point A and to the left of point B, there is no other load. So it will move a constant line up to point B. It arrives at B as 31.73. But at point B, we have a downward force of 20 kilonewton. So if you consider number line, anything acting down, it is a negative. Now that is on y-axis, which will imply it will be 31.73 minus 20, because 20 is going downward. So it will arrive at, this will be 11.73 at point B. And then now between point B and C, I don't have any load. It will remain a straight line up to point C. And then between point C and D, I have a UDL. And this UDL, now what I'll do, at this point C is 11.73. I will calculate. Now, this UDL from C to D is 15 times 2, which is 30 kilonewton. Remember, UDL is acting downward, so it is a negative. Now, that will mean from this point C here, it will be 11.75 subtract 30 kilonewton. That's why we shall end up with the 18.27 kilonewton. Remember, this is a negative because it is below line AG. I told you line AG is our reference line. So this 18, I didn't indicate it as negative because on my key here, I showed you that this is SFD in kilonewton. Whatever is on top is plus, whatever is on bottom is minus. That is why I didn't indicate negative. But for your case, you can indicate negative. Between C and D, between D and E, I don't have any load, so it will remain a horizontal line to arrive at E. When I arrive at E, I have a point load of 25 kilonewton. Because it is acting downward, it is negative. So I take negative 18.27 plus negative 25, which will be negative 43.27. Now, between E and F, there is no any load, so we remain with 43.27 until at point F. When I arrive at F, I have a reaction of 55.27. Remember, this reaction is acting upward, so it is positive. It will mean I have negative 43.27 plus 55.27. This will mean it will take up to 12. So this 12 is above line AG. It is a positive 12 kilonewton. Now between F and G, I don't have a load. It will remain constant 12 until point G. Now at point G, I have 12 kilonewton acting downward, which means is minus. So I had plus 12 minus 12, I will end up at 0. So it will come back to line AG. That is how our shear force diagram will be. Now, we go to bending moment diagram. And in this particular tutorial, I wanted to illustrate to you the two methods of how we can compute the bending moment diagram. Method 1, we shall do the manual calculation, and method 2 or alternative 2, we shall use calculation of area under shear force diagram. Let's proceed with alternative 1. Now, alternative 1 is here. Moment at A, we know it is 0 because it's pinned or simply supported. Then moment at B, now when you consider moment at B, you only take moment due to forces just before B. For this case, you only have the reaction at A and the distance is 1.5. Now, what I want to tell you, the same case I told you, for bending moment, I will have line AG. Whatever is on top is positive bending moment in kilonewton meter. Whatever is on bottom or below line AG is a bending moment in kilonewton meter, but negative. And I know we have different versions of books, but for me, I would prefer whatever you plot or above is a positive, and you should know that a positive shear force will give you a positive bending moment. Then now moment at C, now look at C, but you only look at things that are to the immediately left of C. Now to the left of C, I have what? I have reaction at A, moment due to reaction at A, and moment due to the point load of 20 kilonewton. Now that will be reaction at A multiplied by a distance of 3 meter, 1.5 plus 1.5. Now that is positive, but now minus this 20 kilonewton is a negative shear force going downward, minus 20 times from C, it is 1.5. So I will end up with my moment at C as 65.19 kilonewton. It is positive, you can see. And then my moment at D is equivalent to, now at D, we have three forces. We have reaction at A, we have point load of 20 kilonewton, and we have a UDL that is between C and D. This is how we shall proceed. Now we shall take RA, reaction at A, it's positive, times distance of 5 minus 20 times 3.5. This 20 is minus, it's going downward, but 3.5, it comes 1.5 and 2. So 3.5 minus, this UDL will be 15 times 2 to convert to a point load. But now this point load is acting at the middle. So the distance from D will be 1 meter. That's why we have 15 times 2 times 1, giving us 58.65. Then we go to moment at E is equivalent to, now at E, at point E, we have what? At point E, we shall have reaction A, point load of 20, UDL, and UDL. Yeah, and UDL because we only consider what is there just to the left of that point. So which is RA times 6.5, if you can follow, minus 20 times 5. Then now the distance of UDL has changed. Remember, 15 times 2 is to change to point load, but this 2.5 means D to E is 1.5, and this UDL is acting at the middle, which is 1. So it is 1 plus 1.5, giving us 2.5. Then moment at F, you can choose. Moment at F, I can choose and take negative 12 because this negative 12 is acting downward. So it is a negative shear force. I multiply by distance from F is 1, which is a negative 12 kilonewton, and moment at G is automatically 0. Now, what I want you to understand is that if in shear force diagram, the line is horizontal, for bending moment, the corresponding line will be linearly varying. It will be linearly varying, like you can see. And then when the line, when for bending, for shear force diagram, the line is linearly varying, for the bending moment, it will be a curve. It will be a smooth curve. That is how they correspond. And now, another thing you need to know, where the value of shear force is 0, that is where we have the maximum bending moment. So, like for example, at this between C and D, we have a point where shear force is 0, and between and at point F, now we expect to have maximum bending moment in that regard. Now, if we start plotting, now at point A, I will have 0, and then point B, I will have 47.59, so I can take it at 47.6, and then at point C, I have 65.19, and then at point D, I have 58.65. But remember, we have a value of bending moment between C and D, which will be more than 65.19, because we are saying that is where we have the 0 shear force to expect a maximum bending moment. Now, how do we compute this? How do I determine the value of X here? I will say at this point here, the value of shear force is 0. Now, assume we take the forces from our left end of the beam. It will mean, remember, whatever is going up is positive, whatever is going down is negative. It will mean RA minus 20 minus that force due to the UDL. How do I get it? I take 15 and assume this is now, this distance from C to this point X, I can give it X and say, now RA minus 20 minus 15 times X, because now if I take 15 and multiply by that distance X, I convert it to a point load is equivalent to 0. Then from there, I can solve for the value of X. So once I solve, for example, in this case here, you will find that 31.73 minus 20 minus 15x is equivalent to 0. because at that point, the value of shear force is 0. So I find my x is 0.782, 0.782. Now I can, if I determine the moment at that point, it will be 69.78. Now it will mean my curve will come and then turn at 69.78 and then it continues. Remember, between C and D, it is a curve because we have a UDL, or we have a linearly varying shear force diagram. And then we shall proceed. At E, we found it is 31.245. Since shear force is a straight horizontal line, this for BMD will be linearly varying. The same here will be linearly varying. We have 12 and then it goes back to 0 at G. That is if you choose to calculate manually for each point. But in alternative 2, I will use area under the SFD to calculate the bending moment. This is how we proceed. Now we are using the area. And before we start, I want to tell you, if an area is found on the top of line AG, we take it as positive area. But if an area is found below line AG, I take it as a negative area. This is how we shall proceed. Moment at A is 0. That one is the same, is 0. Then moment at B, look at this B. Between AB, I have a rectangle that measures, it has a length of 1.5 meter and maybe a width of 31.73. Now, like the width is equivalent to value of RA. So I'm multiplying this area here, which is 1.5 times, because the rectangle length times width, 31.73, which is 47.595. The same we had here. Then moment at B, not sorry, moment at C. Moment at C, now we have this one. We take moment at B plus, now from B to C, we have a trapezium, of course, or we can treat it, for this case, I treated it separately as a rectangle and a triangle. So you take moment that was available at B, which was 47.595, plus this rectangle here, BC. Remember, line BC is 1.5. I multiply by, width is now 11.73. I hope you can see it, 11.73, plus area of this small triangle, area of this, which will be given by, remember we determined the value of x here. Now, which means the value of x was 0.782. So it will be a half times 0.782 multiplied by a height of 11.73. No, sorry, moment at C will be equivalent to, sorry, moment at point C will be equivalent to moment at B plus area of this rectangle given by 1.5 times 11.73. But because we know maximum moment occurs at point X, we are interested to know the value of moment at point X. Like we said previously, you will take the sum of shear forces on your left-hand side to point X is equivalent to 0, in which you assume shear forces going down are negative and reactions are positive. So you'll find that moment at X, you need to calculate it because it will give us the maximum value. It will be moment at C, which is 65.19, plus the area of this small triangle, which is a half, times our base. We got it as 0.782 times our height is 11.73. So moment at X will be 69.78. So this 69.78, remember for your diagram, include it here at this apex turning point of our curve. So it will be here. I forgot to indicate. Remember to indicate. Then moment at D. Now look at the moment of moment at D. Moment at D will be moment at C minus area of this rectangle, not rectangle, triangle. Because now my small triangle here is lying below line AG. Because it is below line AG, is automatically negative. So it will be moment at x, which was 69.78 minus a half times 18.27, it is here. Remember, is the value of reaction 18.27 times. Now, total distance from C to D was 2 meter, but from C to X is 0.782. So the remaining distance is 1.218. So you'll find the moment at D is 58.65 kilonewton meter. Moment at E, I will take moment at D. Remember, E still is going downward. So I will take moment at D minus the area of this triangle here. Why? Because it is below line AG. So minus area of this rectangle, which will be 58.65 minus this rectangle measures 18.27 multiplied by 1.5. I'll get that 1.25 kilonewton meter. Then moment at F, now moment at F is moment at E minus the area of this rectangle. So which is 31.25 minus 43.27. 43.27 is here, multiplied by 1. This distance is 1 meter. So which will give us negative 12.02 kilonewton meter. Moment at G will be moment at F, which is negative 12. Then plus, now remember this area here is on the top of AG, so it is a plus. So plus 12, which is approximately 0. So moment at G will be 0 kilonewton meter. Now, the last question we had to determine the point of contraflexion. This is now where the bending moment curve will change from a negative to positive or a positive to negative. Like I told you, this line AG is now the 0, the neutral line. So from this point here, now the point of contraflexion occurs between point E and F. How do you determine it? You can give it like x1, and then you say the sum of moment at x1 is 0 because it is cutting the line, so it has no value, it is 0. And then you can, for example, at this point here, you can use from the right-hand side. I will come and say, remember, this RF is positive because it's acting upward. I will take 55.27, which is RF, times, now assuming it is a x1 distance from F times x1, then minus, I have 12 kilonewton acting downward. Now I subtract minus 12 times. Now see, 12 will have a distance of 1 meter. So you have 12 into bracket, 1 meter, which is FG, plus the x1 distance to the contraflexion point. By so doing, now you equate them to 0. Now the only unknown will be the x1. Once you get the value of x1, you will say contraflexion is either x1 meters from F, or you take 1 meter minus x1 distance from E. Now to determine the point of contraflexion, you say the sum of moment at the point of contraflexion is 0 because it is the point where the moment changes from negative to positive or positive to negative. Now it will have a value of 0. So you give it a distance, like I said, you can say from F, you give it x1, so that now the moment there it will be RF times x1 minus 12 times 1 plus x1 is equivalent to 0. Then from there, you can solve for x1. That will be the point of contraflexion. Thank you very much for your time. Please subscribe, like, and share my channel. And if you need private tutoring in structure, you can reach out to me through the contacts I will attach. Thank you.